G'day, Ben. What fascinating research you're doing. But look, just before we get to that, so tell us what kind of radiation comes from space, potentially dangerous, presumably.
Oh, absolutely. There's so many kinds of radiation that reach the Earth from all sorts of sources. We call it cosmic rays. There can be protons, there can be, nuclei of atoms, there can be gamma rays, and these come from all sorts of astrophysical events. These come from supernovae in the distant universe. These come from black holes, and these predominantly, come from the sun. And you don't want to be doing a lot of interplanetary travel if you're on a spacecraft traveling to Mars without radiation shielding. This is one of the big issues that people are worried about getting astronauts to Mars, is because there's such a harsh radiation environment in space. We're protected from it on the Earth by our magnetosphere. So the Earth has a magnetic field that extends far out into space, and this deflects a lot of charged particles so that they only really arrive on Earth at the poles, at the aurorae. Nevertheless, if we didn't have that magnetosphere, as other planets don't all, then we could be in real trouble.
And every now and then we get a big burst that our magnetosphere doesn't protect us from, right?
Oh yeah, no. So one of the big issues is solar, we call it coronal mass ejections. These can dump a huge number of particles out into interplanetary space from a giant stellar flare. And so when these hit the Earth, these can stream down on the poles of the Earth. Really, really extreme ones can actually give you an aurora as far south as Hawaii was recorded, the Carrington event, the biggest ever recorded solar flare. And yeah, I mean, these can cause issues for satellites in orbit, and indeed for the electrical grid on Earth, because they distort the magnetic field. And this drives currents in the transmission lines and transformers on the Earth, which can be very dangerous.
And so that Carrington event happened in the past, right? What happened if that, when we're in the pre-electronic era, right?
Totally.
So what happens if we got one today? What would happen?
It would be really bad news. So the Carrington event is the biggest ever recorded with scientific instruments, but this occurred in the Victorian era, when nevertheless we weren't very dependent on electrical, devices. We didn't have any satellites at all. Didn't even have planes. We think that if the Carrington event occurred today, it could destroy large amounts of electrical infrastructure on the Earth and satellite infrastructure, unless we took careful steps to protect from it. If you had careful insulation of, sensitive electronics. Okay. So it's not even clear that the Carrington event's the biggest thing that could happen. And this is what I'm researching.
I was going to say that nicely brings us to your research. So it'd be great, presumably, if we knew what kind of events had happened in the past, but we don't know about that at the moment.
Very much.
You're about to find out.
Well, hopefully. So what we're going to use is the Earth's forests as a giant telescope that has been, observing for 10,000 years. Because every year, trees lay down a growth ring. And you can date this very precisely because people have archives of trees where each growth ring, a good season might be, longer or shorter than another season. And this is like a barcode. And so you can actually line up a segment of tree rings with a big archive of known tree rings and get a precise date for any ring going back 10,000 years, right? What's also cool is you can measure the composition of the wood at that year. And what this allows us to do is to measure the radiation environment of the Earth in the year in which the tree ring was laid down. Because cosmic rays striking the Earth's atmosphere give rise to radiocarbon, carbon-14. This is what we use for carbon dating archaeological sites. Now, it turns out that you can have some years where you get more radiation that produces more radiocarbon. Some years you have less. And so this means that actually the amount of carbon-14 fluctuates. And so we measure this by going into tree rings where we know the exact date. So we don't need to carbon date anything. We can measure just from the barcode of the tree rings. And we've also got a sample of wood from that year. And then we do single year measurements in order to figure out what was the amount of radiation hitting the atmosphere 1,000 years ago, 10,000 years ago. Now, people have been doing this for some time, using tree ring data to build this radiocarbon calibration curve. They were mostly thinking of it as being for archaeology. And once the instruments got better, so you could do better time resolution, you could do single years instead of decades, and you could do really, really precise measurements, a Japanese team in Nagoya, led by Fusa Miyake, discovered something really shocking. That once you had really, really good data, sometimes you had these single-year huge spikes in radiation. And we don't know what these are. And so Miyake found
They sound dangerous, though, potentially dangerous.
Yeah, oh, very, very. So Miyake found one initially, and then found 3 more have been found. And the biggest of these occurred in 774 AD. There was another in 995 and a couple in further back in time, like 5000 BC, right? And we just don't know what they are. There's one theory that this is a kind of extreme solar event. And this is, I think, what most archaeologists believe. So this might have been 40 times bigger than the Carrington event. Now that would be shockingly dangerous, you know, for satellites, for electrical grids. And we really don't know how to predict it, you know, whether it's the sun or whether it's something else, and what we would do about it if it actually happened today. They seem to occur about every 1,000 years, but you imagine doing an insurance policy on this, right? So once every 1,000 years is 1% per decade. Okay, so that's probably not going to affect us, but a 1% chance of taking down our entire satellite grid, that's something to worry about.
And it's not just the satellite grid, presumably. I mean, you know, we run on electronics these days.
You know, people on aircraft would receive radiation doses. Yeah. So the issue is that we don't know whether it's the sun at all. That's the leading theory, but other people have suggested it's nearby supernovae in the galaxy, you know, high energy radiation from these supernovae. Now, I don't think it really is. I've done a little bit of research and it doesn't seem to fit with all of the data. On the other hand, some people have suggested these are magnetar bursts, so intense bursts of radiation from highly magnetized neutron stars. So the dead remnants of stars, you know, 10 kilometers in diameter, but with the mass of a whole sun, with tightly wound magnetic fields that sometimes unkink, reconnect, and give off these huge flares. So that could do it. Magnetar bursts have even given issues for satellites in the past, but this would have to be closer and bigger than any we've ever known. And so I think really the jury's still out on what these are. And what I'm interested in doing is applying modern statistical and computational sort of machine learning, Bayesian statistics sort of techniques to apply to these data and get a really good estimate of when these happen, how often, how big they are, how long they take, because that'll tell you if it's a solar flare or a magnetar burst, right? And so that's why I'm really excited to be doing this research using modern computational techniques across archaeology, astrophysics, to find out something that we really don't know the answer to, where the answer could be vitally important.
Well, it sounds, I mean, it's fascinating research, but really important as well, right? So if you can sort of narrow down the source of that radiation and the sort of size of the radiation, at least we have a chance of trying to protect ourselves if one of these things comes.
Very much so. It could be that this is, you know, something where we can understand how it interacts with the Earth's magnetic field. It might be that the sun is doing it and there's some indicator. It might be that a nearby magnetar is doing it and we can find that magnetar and monitor it. You know, there's all sorts of ideas theoretically about what these would be. And if we knew what the answer was, we could start to prepare for and to mitigate the effects of any of these events. If we knew what they are.
How you've got you know, the Big Questions Institute fellowship to research this. How important do you think those kind of fellowships are for sort of this big picture research?
I think that's hugely important. It's really important that often research like this, which is interdisciplinary, you know, it's very hard to go to the Australian Research Council or any other, you know, institute and say, okay, I want $1 million to research something that's in between archaeology and astrophysics, which has a 1% chance of affecting anyone in the next decade. That's very hard to actually pitch, even though it's very, very important, right? Here is a complete mystery where we don't really understand what's going on in any way, and we can't tell you what the results of our research are going to be. Well, often, really, research councils want to fund, we know what the results are going to be. We're going to measure this parameter of this understood theory very precisely, and it will involve all specialists in one particular subdiscipline. And, you know, that's a very easy grant application to put up. something which is interdisciplinary, something which is a little bit high risk, high reward, that doesn't get up. And so the BQI is a really, really important resource to be able to ask very hard, unusual, interdisciplinary questions with important answers, but which don't fit into existing categories of, is this astronomy? Is this archaeology? Is this, computer science and statistics, or is this, risk management, for the Earth? It's very hard to get those proposals up at other venues.
Well, look, good luck with the research. Good luck with it, and really looking forward to finding out what you discover.
So am I.